Hey there everyone, welcome to this video in the hand calculation series. In this video we're going to be talking about the electron output factor. So we can start with the definition of the electron output factor, or EOF for short. So this is the definition here. It's a ratio of doses. One is measured with some cone and cutout size, and then it's always normalized to the dose measured with the reference cone. And I will draw out the geometry over here on the right. You can see here in red, the red triangle represents the reference cone, and then the dashed black triangle represents the cone and cutout that you are measuring the output factor for. And so you always measure at the reference SSD, which is typically 100 centimeters, and you always measure it at a depth of D max for the given radiation beam. And yeah, it's just a ratio of the doses measured under these two circumstances. And here's an example of some of the cutouts that you might use, that you might insert into the cone to determine these output factors. So they're just, square cutouts, and these are what are actually used to measure the output factors and what are used to actually tabulate the beam data. And here is an example electron output factor table. And so you have your beam energy across the top, and then you have your different cone sizes with the different cutout inserts as well. And you can see here that the reference cone for this beam data was the 15 by 15 cone. So that's where the electron output factor is actually equal to 1. And then every other cone cutout combination is always normalized to the dose measured with that 15 by 15 cone. But this is just an example showing an electron output factor table. Another interesting thing about this table is that there's no output factors tabulated for cutouts less than 3 by 3. And the reason for this is that with smaller electron fields, like smaller than 3 by 3, we really run into issues with penumbra, and basically the whole field is penumbra in this case, and it's really hard to predict what the electron output factor will be. It's really hard to measure, and it might depend on the detector you use as well. And so in cases where the lesion is really small, it might be good to use an orthovoltage machine, which back in the day was pretty common, but are actually pretty rare nowadays. But I just wanted to point out that the electron output factor is really difficult to quantify for fields that are smaller than 3 by 3. So what if we have a non-square cutout? In the previous table, all of those electron output factors were for square cutouts. But in the case where we have a rectangular cutout, we would just take the geometric mean of the square cutout output factors with sides equal to that of the rectangular cutout. So if we have a rectangular cutout of sides x and y, we just find the output factors for the square cutout of side x and the square cutout of side y, and just take the geometric mean. And this is different from photons, right? Because with photons, we are calculating an equivalent square field size, but with this, we're just basically doing a numerical averaging technique and getting the output factor for our rectangular cutout in that way, rather than calculating an equivalent square. Similar to the equivalent square concept, this is a concept that was empirically determined and has been used in the radon community for quite some time now. And that is it for the video on electron output factors, so thank you for watching.